In the last class, we spoke about electrodynamics of charged particles, and we spoke about some applications of electric and magnetic fields, and one of which is the velocity selector. We moved on to the mass spectrometer, moved on to the cyclotron, which is used in producing energetic particles in medical diagnosis and treatment. Let me get my pointer. They contain two semicircular discs, which the signal that comes into this disc, they alternate. When this is positive, this will be negative. So the particle to be accelerated is injected in this point P. Once it's injected in point P, it comes into, okay, no, this semicircular disc is labeled D1, the other one is D2. When it's the part in which the particle will travel is the dotted line we have on this figure. And when the particle is injected through the center into, let's say, D2, the potential difference between D2 and D1 will make the particle to accelerate and spiral out of D2. When it's going towards D1, the voltage will alternate. That is, before D2 was positive while D1 was negative. Now it will now change. The voltage would alternate such that the plate that was formerly positive will become negative, and the one that was negative will become positive. And that will cause the charged particle to further accelerate. And the charged particle will keep accelerating as it's coming out of a semicircular disk. The potential difference changes. I mean the sign, the sign when we call this, I mean the polarity. Yes, I want to use the term polarity. The polarity changes. So when it leaves D1, before it enters D2, the polarity would have changed to make it accelerate further. When it's leaving D2, the polarity would have changed before it enters D1, so it further accelerates. And whenever it's leaving any semicircular disk, whenever it's leaving any of the Ds, the polarity will change and the particle will accelerate further. And when the particle leaves through this point, it leaves with very large energy. It leaves with large acceleration. So, and the same thing is described here. They are just the same thing like what I've said. The particle will enter through this disk. The disk are actually called Ds. They're actually called D. So the plural is Ds. And once you launching a charged particle through the center, there is potential difference set up between the Ds. And since this plate is this plate and this plate, they have different charges, then there is potential difference in between them. Electric field is set up between them, and the particle enters the first D. It is accelerated on coming out of the first D. Before it gets to the second D, the polarity has changed. And when the polarity changes, it accelerates further. Before it comes out of the second D, the polarity will change again back to this previous state. It enters this first D again, and before it comes out, once it comes out, before entering the next D, there is another change in polarity. So it will keep accelerating until through the dotted line until it comes out as a as a particle with large energy, a particle with very large velocity, which is used in medicine and different scientific research. So another application is the galvanometer. The galvanometer, like we have spoken about in most of our discussion, it's a device that measures very tiny currents. It is not designed to measure large currents. Just 1 minute, please. Sorry for the break. I had to stop some unruly students from stopping. Okay, so we've spoken about the galvanometer as an instrument, a measuring instrument that is sensitive to tiny current flow. And we spoke about it while talking about the Wheatstone bridge, the meter bridge, where we spoke about an arrow at the center that deflects and to the right when current is flowing to the right, and deflects to the left when current is flowing to the left. So the galvanometer can be adapted to work as a voltmeter. It can also be adapted to work as an ammeter. As a voltmeter, it will begin to measure voltages, and as an ammeter, it can also be useful in measuring large currents. You must have observed that whenever you have a circuit and you want to connect an ammeter, when you have a circuit of, let's say this is a battery and connected to a resistor, when you want to calculate the current flow, you usually connect your ammeter in series with the circuit. If you want to determine the current that will flow through this resistor R, you are expected to connect your ammeter in series with the circuit so that the current that flows through the resistor will also flow through the ammeter. But whenever you are talking about voltages, you want to measure the voltage or potential difference across this resistor, you are most likely, or you are expected to connect your voltmeter in parallel with the resistor. So how do we make a galvanometer to work in this way? The galvanometer is designed, usually referred to as G. The galvanometer, or described as this, the galvanometer is designed to detect small current flow, just small current flow. So to use the galvanometer as a voltmeter, a resistor is placed in series with the meter. A resistor is placed in series with the meter. So that means that when we don't have a voltmeter, all we have is a galvanometer, and we want to measure current flow. We don't have a voltmeter, but we have a galvanometer and want to measure the potential difference across this resistor. That means we can replace this with a galvanometer. Let me take another color. We can replace this with a galvanometer and also add another resistor so that it will limit the current that will flow through the galvanometer. When we connected the voltmeter across the resistor, current still flowed through the voltmeter. So by connecting the galvanometer in series with a resistor, now both of them across the resistor we are measuring, the resistance we are measuring, it will limit the current that will flow through this galvanometer. And this resistor is called the shunt resistor. The shunt resistor. So, and it's usually the resistance value is usually large, so that the current that will flow through will be limited. So when we want to measure the current flow through an ammeter, or we need an ammeter, but all we have is a galvanometer. To use the galvanometer as an ammeter, a resistor is placed in parallel with the meter. As this, a resistor is placed in parallel with the galvanometer. So that means that I don't have an ammeter, I have a galvanometer, and I want to measure current flow. Then I can put my galvanometer here and put another shunt resistor in parallel with the galvanometer. But this time around, this shunt resistor is going to be one of very low resistance. So that as the current is, the reason why it has to be low resistance is because when current is flowing from the battery, a huge fraction of them will prefer to go through the path of low resistance, while very tiny fraction will flow through the galvanometer. And that will help you to measure the current. So the nature of the resistors you have used as shunt will help in calibrating your galvanometer to work as either a voltmeter or an ammeter. So let's look at the working principles of a galvanometer. It's also based on electromagnetic interaction between current and magnetic field. So that means that current flows into the galvanometer, and since it flows into the galvanometer, into a coil in the galvanometer, and the coil in the galvanometer is placed within a magnet. You can see this is North Pole, this is South Pole. So that means because we have a magnet here, we have magnetic field present around the coil. When you connect the galvanometer to take measurements, current flows into it. And since current flows into it, it means electrons are in motion through the coil. And since electrons are in motion through the coil, we should expect the electrons to exhibit magnetic features. And since they'll be exhibiting magnetic features even in the presence of a magnetic field, then there should magnetic force, interaction between the magnetic force created by the magnetic field present here, that is the North and the South Pole, and the magnetic field created as a result of the motion of electrons within the coil will cause the coil to deflect, meaning that it will cause the pointer also to move, because the pointer we have here that is showing on our measuring scale is connected to the coil. So as the coil turns, the pointer also moves, and we should expect it to keep moving. But we also have a restoring spring here that will prevent it from moving continuously. This restoring spring is to stabilize the pointer. The restoring spring will prevent the pointer from just moving down to full scale deflection. The restoring spring is the work is to balance the magnetic force created as a result of current flow. When tiny current is flowing through, we should expect tiny deflection. When large current is flowing, we should expect large deflection. Why? When tiny current flows through, tiny magnetic field is created as a result of the tiny current flow, and that means tiny magnetic force is experienced by the coil. Be it tiny, be it large, since it's a force, it should keep moving. But for the fact that there is a restoring force here, the work of the restoring force is to return the pointer back to zero, is to return the coil back to status quo. So when current is flowing into the coil is moving, the pointer is deflecting. The work of this restoring spring is to strike a balance. Is to, if the force is large, if the force created as a result of the current flowing to the coil, if it is large, it will move very far. It will extend the spring, the restoring spring, more than if the current flow is small. You should have seen that while working on Hooke's law in your practical classes. That is, when you apply small force, you extend the spring a bit. When you apply large force, you extend the spring further. So the work of the spring is to ensure that you don't have full deflections at all time. Is to check the force and now trying to measure the extension as a result of the force that is applied on the spring. And where is this force coming from? It is coming from as a result of the current that is flowing into the coil of the galvanometer, creating magnetic field and interacting with the external magnetic field that is permanently within the surrounding the coil. So the point of equilibrium is the measurement that you take. The point of equilibrium between the magnetic force created as a result of current flow into the coil and the restoring spring tells us this is the actual current that is flowing into the galvanometer. So, and that requires calibration anyway. And when current is disconnected, when there is no current flow into the galvanometer, it is the work of the restoring spring to return it back to zero. So in technical words, the small spring supplies a counter torque. And when the two torques cancel, that is when the torque created as a result of the force, the magnetic force in the coil. When the magnetic force in the coil balances the force in the spring, then you can say the two torques have cancelled when the coil is not moving, when the coil is stationary, when the coil is actually maybe taking the measurements, let's say from, so we can say the two torques cancel and there is equilibrium. So let's move forward. So let's talk about Maxwell's equations. I think I have some messages here. Just like that. Okay, Ayomide of physiology, please see me as regards the calculator. Okay, we cannot talk about the interaction between electric and magnetic fields without discussing the Maxwell's equations. The Maxwell's equations tell us things we have somehow encountered in the course of, or will still encounter in the course of this course, or during this course rather. So there are actually 4, and of the 4, they are of 2 variants. This is the differential variant and the integral variant. These 2 equations are actually saying the same thing. This is saying that the divergence of the electric field is equal to the ratio of the charge density to the permittivity, charge density to permittivity. So, and it's telling us that the total electric flux through any closed surface equals to the net charge inside that surface divided by the permittivity. So Gauss' law relates the electric field to the charge distribution that creates it. It relates an electric field to the charge distribution that creates it. So, and that is, it can also be written in this form, an integral of the electric field and product of change in area. So we have a Q over epsilon naught, where Q here is the charge, rho here is charge density, and the charge density is here is, it means Q over V, charge over volume. This is volumetric cubic charge density. Well, coming to the second law, which is Gauss' law. Okay, the first law is the Fox equation is talking about Gauss' law. And the second equation is talking about Gauss' law in magnetism. And this second equation is telling us that the number of field lines that enter a closed volume must be equal to the number that leave that volume. The number of the magnetic field lines that enters a closed volume must be equal to the number that leave that volume. And this implies that magnetic field lines cannot begin or end at any point. And for us to say it begins or end at any point, it must mean that we should have magnetic monopoles. And in nature, there is nothing like magnetic monopoles. We have spoken about the electric charge to be, we can have positive, where the lines, the field lines radiate or emanate radially outwards. Let me put the arrow. We can also have a negative charge, also having field lines with the lines of force coming inwards. But we cannot say we have a magnet and say this is North Pole. There is nothing of such in nature to say this is a North Pole and this is a South Pole magnet. It's not possible. These are not possible. The only, in nature, the type of magnets we have are in dipoles. We'll have the north and the south existing together. So when the lines of force of the North Pole is going outwards, the ones connected to the south are pointing inwards. So if you now take this magnet and you enclose it in a particular volume, the number of lines that go out must be equal to the number of lines that come in. And that will mean that the divergence, as it's written here mathematically, the divergence of the magnetic field vector is 0. And similarly, the closed integral of the magnetic field vector dot differential of the area vector is equal to 0. So the magnetic field flux is, in short, the net magnetic field flux. When we say net, we are talking about inward minus outward, just like we spoke in Kirchhoff's law, where we're saying the algebraic sum of current entering a loop is, we could have as well said, the net current entering a loop. It's just like your account balance. Even if hundreds of if 500 naira should enter your account and 480 naira leaves your account, you cannot say that you have 500 naira. You check the net, and the net will be the one entering minus the one leaving. So the net can be said to as good as entering minus leaving. The net magnetic flux through a closed surface is 0. So let's move on to the third Maxwell's equation. The third Maxwell's equation is talking about Faraday's law. It's talking about Faraday's law. And the Faraday's law of electromagnetic induction, it describes the creation of electric field by changing magnetic flux. The creation of electric field by changing magnetic flux. One consequence of Faraday's law is the current induced in the conducting loop placed in the time varying magnetic field. So you must have learned in secondary school that Faraday's law says that the rate of change of magnetic flux is directly proportional to the induced EMF. That is what we have here. The rate of change of magnetic flux. This is dB dt. That is dB dt. No, dB dt, the dB dt is actually a rate of change of magnetic field. And what we have here is called curl E. It's called, mathematically it's called curl E. And curl E is a cross product of the grad operator and the electric field. The cross product of the grad operator and the magnetic field. So the EMF, which is the line integral of the electric field around any closed path. So this integral, when you have an integral having a circle, is called is a closed integral. So now we are talking about a closed path. It's equal to the rate of change of magnetic flux. So this is exactly what Faraday's law we learned in secondary school is saying. The rate of change of magnetic flux. Phi, capital Phi here is magnetic flux. But the rate of change of magnetic flux is is equal to or is directly proportional to the EMF. And let's move to the last Maxwell's equation. That is the Ampere-Maxwell's law. It tells us that the line integral of the magnetic field around any closed path is the sum of mu naught. Mu naught here should be the permeability of the medium. Just like we call epsilon naught to be the permittivity of free space, mu naught is the permeability of free space. So the sum of mu naught times the net current through that path. And just like we have a epsilon naught mu naught times the rate of change of electric flux through any surface bounded by that path. So it describes the creation of a magnetic field by changing electric field and by electric current. So we have a changing electric field. This is electric flux. Phi subscript E is electric flux. The phi, the T, tells us that the electric flux is changing with time. So the product of epsilon naught, mu naught, and the changing electric field, in addition to the permeability, product of permeability, and the electric current, gives us information of the creation of magnetic field. So this is also the differential variance and the integral variance. And just like if you look at both of the four equations, one is two of them are dot products of grad and the field. So we have grad dots products, and the other two we have, and in the other two we have the cross products. We have cross products, that is the call operation is taking place. And another thing you should also notice that two of them is talking about the electric field, while two of them is talking about magnetic field. So when we are talking about electric fields and magnetic fields, we are talking about electromagnetism. And Maxwell's law, the knowledge of Maxwell's law has helped in many areas, like transmission of electromagnetic waves, calculation of speed of light, and many applications in electronics. So still on the Ampere-Maxwell's law, which is the fourth Maxwell's equation, J here is current density. J is current density. I've defined sometimes down here. So the current density can be defined as product of sigma and E, or we can also call it I divided by A, that is ratio of currents and area. We can call it current over area, that is current flow through a particular channel divided by the cross-sectional area of the conductor carrying the current. We can also call it product of sigma and E, and sigma here is the area charge density. Sigma area charge density and the electric field. And D here is electric displacement, which is a product of the permittivity and the electric field vector. So the electric displacement D, just like electric field vector E and current density, they are vectors. So that means that they have direction, and their direction is considered in making reasonable decisions.